If we take a chain rule, if we apply a chain rule, then we get equation which look like this, and this A is a Jacobian matrix. And remember that I put this vector over variable q just to show that the q is not a scalar anymore. But usually when you do linear algebra or matrix algebra, you actually make it bold. When it is bold, it looks like a column vector or a matrix. So here I have written the general form of vector equation. This is a vector equation. So my idea is to linearize it, since this is a nonlinear equation. Why it is nonlinear? Since there is one term over here which is unknown in terms of unknown, so it is a nonlinear due to this term. So what we do, we actually linearize it. If this video is a bit longer, then you should watch it completely to understand the concept. So what we do first of all, we introduce a vector q which is written as some fixed state q naught, and there is some perturbation. What does it mean? It means that when we have some fixed state, something like this, and if you just perturb it, something like that, this quantity which is at fixed state is called u naught, for example fixed velocity u naught, and that quantity is called the perturbation, a small change, then u will be equal to u naught plus u tilde. For example, you are measuring this quantity from here to here, then this will be u will be equal to u naught plus u tilde. This is u naught, this is u tilde. So this whole quantity will be u is equal to u naught plus u tilde. So that's what we call it, perturbation. So I put this value, this perturbation, into that equation everywhere, wherever I see q vector. But let me just go back and write this equation in the conservative form. This is called a conservative form, since it will be easier to convert the conservative form. This is conservative form since we have this matrix. We did not find the Jacobian until now, although I introduced the Jacobian in previous video, but we did not know how to find this Jacobian, and we will find out very soon. So what I did, I just went back to the conservative form of the conservative form of PDE. Now I put this Q vector into this equation. So that will be equal to partial by partial t Q naught vector plus Q tilde vector plus partial by partial x f Q naught vector plus Q tilde vector is equal to 0. So we put it, the Q vector is equal to the fixed state to the and added perturbation. Now since this Q naught vector, which is a fixed state, it is not varying, so this will equal to 0. So we get partial Q tilde vector by partial t plus partial by partial x f Q naught vector plus Q tilde vector is equal to 0. Now this is very important step, how to open this function. Remember that Q naught vector is rho naught and rho naught u naught. So this Q vector becomes, when it is Q naught, it becomes rho naught and u naught. So here I can apply Taylor series, and if I go back to the calculus 1, the Taylor series look like this. F x plus h, f of x plus h, f dash x. Since my idea is to retain only linear term, so I write order of h square. Similarly, if we write equation in multivariable calculus, x plus h, y plus k, then this will be equal to f of x y plus h f of x plus k f of y plus so on. We have some other hk and f of xy term, etc. But here we have f, which is q naught rho naught plus, if I add these two vectors, we get rho naught and rho naught tilde. Similarly, we have rho naught u naught plus, and we have rho naught u naught tilde. It looks like this is equal to, so we apply Taylor series. So you know that, as I already discussed, f of x, for example, x naught plus h, you write on the right hand side this f of x naught. So here you have to write f of q naught vector. This quantity will be over here like this. Maybe I write rho naught u naught, and this becomes f of q vector, q naught vector. So we write f of q naught vector. Then we have the next term, which is a linearization. Since the generalization of first order partial derivative, generalization of calculus 1 is Jacobian, we write delta f and we find the value of delta f at q naught. Maybe I repeat again f of x naught plus h, f of x naught plus h, and you find the derivative of f with respect to x naught. Since we have two terms, we get the Jacobian matrix. And we multiply this Jacobian matrix with q tilde. Okay. Maybe I repeat again f of, just to make sure that you understand it completely, f of x naught plus h in calculus 1, f naught plus, and you know that there is x naught plus h minus x naught and f dash x naught, and if we write it down plus, you see that this will be cancelled out and you get f dash x naught. This f dash x naught has been replaced with Jacobian, and this h has been replaced with q vector, since you take you subtract rho naught, which is actually q naught vector plus q tilde minus q naught vector, and you get q tilde. There I put it the dot product over here. Since this is a matrix, and if you have this vector, and you should put the vector over here so that it looks like a dot product, or maybe some product, since there is no dot product of the matrix and the vector. So we have delta f dot q tilde. Okay. So it means that I will replace this term, which is actually f of q naught vector plus q tilde vector, with the right hand side. So let's put it into the equation. Which equation? This equation, or maybe over here. Video is a bit longer, or maybe over here. Video is a bit longer, and you must see the complete video, otherwise this confusion will remain everywhere in future. So partial q tilde by partial t. Now this Jacobian is a scalar quantity. This Jacobian is a scalar. Why it is not a, it is a fixed quantity, I should say, since you are finding Jacobian at q naught. This Jacobian will come outside partial f tilde by partial q, partial f vector by partial q vector. So this becomes partial f by partial q vector, and it has been obtained at q naught vector. And the next quantity is partial q tilde by partial x. I hope you understand that point. So we just replace, since this is just a scalar, this is just a fix, so it will come outside, and this q is a variable and we put it over here. And remember, so this dot product, one should understand what is the meaning of this dot product, and it just says that you are multiplying these two matrix and vector. And since it is a, maybe you can remove the dot product as well, it is also possible. So we have converted the actual equation, this equation or that equation, into the perturbation form. Now there is a variable, I should put the vector over here. This is a perturbation equation. Perturbation equation. So since this video is a bit longer, I will continue working on that in the next video.